Hi everyone, let's understand some formal definitions of automata. Here we will be defining formal definition of finite automata. Finite automata or finite state machine is phi tuple, means that kind of machine consists of phi entities. For example, set of states. Each state takes some input. Input is available in the set of input symbols sigma. Based on the received input, one state is moving to another state as per the transition function, and these set of states consist of starting state and final state. Here starting state will be only one, but there may be more than one final state. Let's understand this formal definition of finite automata with this example. In this example, this is a finite automata. We can call it as a capital M. So this is the machine. How many states are there? Q0, Q1. So what is the set of states? Set of state we can call it as a Q0, Q1. What are the input symbols? 0 and 1. So we can call it as like this, 0, 1. Transition function we will see in the next slide. Starting state here is Q0. And what is capital F here? Set of final state. Here only one final state. We have seen many examples where there are more than one final state. So starting state will be only one, but final states will be more than one. That's why it's defined as a set of final states. Now, based on the transition function, in all the automatas, these four things will be the same. These are not going to change, but transition function is going to vary, or we can call it as there is a variation of transition function. Due to that, we can define or we can say type of finite automata. Like we have DFA. So as per the transition function, if it is deterministic in nature, we can call it as a deterministic finite automata or non-deterministic finite automata, or we can see it as a epsilon NFA. So what are the formal definition of this, or what is the transition function in these kind of automatas that we will see. First, DFA, deterministic finite automata. As we know, what is deterministic? Deterministic means what? There will be only one transition for each symbol from each state. For example, in this case 0, 1. Input set consists of 0 and 1. How many states are there? States are 2, Q0, Q1. This is Q0 and Q1. Now in this case, from Q0, there is a one transition for 0, there is a one transition for 1. From Q1, one transition for 0, one transition for 1. So there is only one transition from each state, and it should be there. If any transition is missing, we cannot call it as a deterministic. So there must be one transition from one state. Now how we can define this? For example, here Q0. Q0 is reading 0. Q0 reading 0 going to Q1. So I can say like this. Q0 reading 0 going to Q1. So I am just taking this notation. Q0 reading 0 going to Q1, or I can say Q0 reading 1. Q0 reading 1, it's going to Q0. So I am writing here Q0. By reading 1, it's going to Q0. Or I can say Q1. Q1 reading 0. Q1 reading 0. It's going to Q0. Then Q1 reading 1. It's going to Q1. Here, by reading one symbol, it's going to only one state. See, for 0, only one state. For 1, one state. For 0, one state. For 1, one state. All these are set of states, Q0 and Q1. The set of states are represented by capital Q. So can I say here capital Q? The 0, 1 is nothing but set of input symbols. So can I say sigma? Any state reading set of inputs. It's going to where? It's going to Q1, Q0, Q1, Q0. It's going to unique states. So can I say again set of states? Because these set of states are same as this set of states. So here first symbol is for Q. I will write here separately set of states, reading some input, so sigma, going to set of states, so again q. So this is what a transition function. So transition function for DFA is like this: set of states, reading some input and going to some set of states. And when this transition function is followed or implemented, we call it as a DFA. Here one state reading one symbol going to only one state. That is the point of deterministic. There is no single state by reading one symbol going to multiple state. There will not be scenario like this in DFA. There will be only one state. Similarly, we will see what is non-deterministic. Suppose this is a DFA, or we can call it as a machine. Here set of states are same, Q0 and Q1. What are the input symbols? Sigma. It consists of 0, 1. If I write here, for example, Q0 reading 0, it's going to where? Check here. Q0 reading 0 going to Q0, or Q0 reading 0 going to Q1. So it's going to more than one state. Q0 after reading 0 going to Q0, Q1, or I can say Q0. There are no transition for Q0, so I will take Q1. Q1 reading 0 going where? There is no transition for Q1, so I can say 5. Similarly, Q1 reading 1 going to where? Q0. By reading 1, it's going to Q0. Similarly, I can also write, for example, Q0 reading 1. There is no transition from Q0 for 1. So can I say 5? Yes. If you observe in this scenario, one state reading one symbol going to more than one state, and that is what non-deterministic behavior. Or by reading one symbol, it's not going anywhere. It means what? By reading one symbol, one state can go to 0 states, 1 state, or more than one state. That is not defined, but there is some restriction for that. How many state it will go, that we will see. But try to understand the behavior of non-deterministic. Non-deterministic means what? By reading one symbol, one state can go to nowhere, or 5 state, or 0 state, dead state you can say, but we can say nowhere. Or by reading one symbol, one state can go to more than one state, maybe 1 state, 0 state, 5, or more than one state. That is non-deterministic behavior. Now, where we can restrict this, to how many states it can go? Suppose there are 2 states. How many possibilities? It can go to nowhere, means 5, like this. One state can go to the Q0, for example, it will go to the first state, or it will go to the Q1, or it will go to the both, like here Q0, Q1, here. So apart from these 4 possibilities, it will not go anywhere. If there are 2 states, for example, if there are 3 states, again their possibilities will increase. So what is this? This complete set is nothing but the power set. This power set is a concept from the discrete mathematics. You might be aware of this. What does power set says that? Now how many number of states here? 2. So 2 raised to capital Q. What is capital Q? Set of states here. Then what is 2 raised to Q? If Q is Q0, Q1, this set, whatever I have written here, this is nothing but 2 raised to Q. 2 raised to Q consists of 5 null. If there are 2 states, then it will go to the Q0, it will go to the Q1, or it will go to the both Q0, Q1. So power set consists of all subset. That is what power set definition. It will go nowhere, it will go to the one state individually, or it will go to the both the states combinedly. That's what definition of power set. Now how we can define this? See, one state reading one symbol. Yeah, so one state means what? Set of states, this Q0, Q1, all the set of states. It's reading 10, 10, so it's reading input sets. It's going to where? In the last definition I told you it's going to only one state in case of DFA, but in case of DFA it's going to more than one state. But where it's restricted? How many states? It's a power set, 2 raised to Q. So I'm writing here 2 raised to Q. And this defines our delta for NFA. So delta Transition function for NFA is set of states reading input and can go to the power set of states 2 raised to q, that is defined here. And this is formal definition of non-deterministic finite automata, NFA. Now in this definition, all input symbols are nothing but this 0 and 1, whatever is given, set of input symbols sigma. If in this case, this input symbol consists of few more symbols, for example, let me define then epsilon non-deterministic finite automata or epsilon NFA. What does this says? Same definition. If suppose here q consists of q0, then q1 and then q2. What is sigma here? As usual, here sigma consists of 0 as well as 1, and here epsilon is also part of input set, because by reading epsilon q0 is moving to q1. So this epsilon is also part of this sigma input set. This is our epsilon. How we can define this? Let me explain that first of all. q0 reading what? 0 going to q0. q0 reading epsilon going to q1. q0 reading 1 going to nowhere. So if it is not going anywhere, means it's what? It's a non-deterministic behavior. It can go to more than one state also. For example, if you want to know, I can connect like this. By reading 2, q2 by reading 2 going to 2 states. Let me write here. q2 by reading 2, for example, it's going to q1 as well as it's going to q2. So q2 by reading 2 going to q2 as well as q1. So similarly we can write for q1 but not required. This is sufficient to define this epsilon NFA. What does this says? See, q0, q0, q2, q1, all these are states. What are they reading? They are reading 0, 1, 2 as well as epsilon. Where is 0, 1, 2? 0, 1, 2 or what are the symbols? Here input set consists of 2 also. Let me correct it, 0, 1, 2. So all these states reading epsilon, plus in addition to epsilon, it's reading epsilon also. In addition to this sigma, it's reading epsilon also, because this is epsilon NFA. Transition label are epsilon also. So I can add here, this is the union sigma. So here set of states reading input set sigma, union epsilon also, and going to where? It can go to one state, it can go nowhere, or it can go to multiple state. That I have explained while defining the NFA. That is nothing but power set. So definition of NFA and epsilon NFA is same, except in the epsilon NFA we have added this epsilon here, and this defines transition function for epsilon NFA. So this is DFA transition function. This is NFA transition function where change is 2 raised to k, and this is epsilon NFA where change is epsilon here as a part of input set. Let me revise this here. So our finite automata, or I can say finite state machine, is a phi tuple. Set of states, set of input symbols, starting state, final state. Only change is in the transition function delta in all three definitions. What is that? In deterministic, one state read one symbol goes to only one state. That's why here only one state, q. In NFA, it's a non-deterministic behavior. By reading one symbol, that state will go nowhere, means 0 states, phi. It will go to one state or it will go to 2, 3 based on this power set 2 raised to q. This 2 raised to q defines NFA. Same in the epsilon NFA also. It will be same. NFA and epsilon NFA are exactly same, except here input set symbol is sigma, here also sigma, but in addition to that we have epsilon. That's the change, and that defines our epsilon NFA. So already we learned, we designed definitions, problems, automatas for this DFA, NFA, epsilon NFA, and these are the formal definition. As we already learned how to design automata, so this will be very easy to understand. In the next few examples, we will see conversion of epsilon NFA to DFA. Thank you for watching.